the pilot production of very low volume components, if the volume of the component to be produced, or batch production if you want to have, then you can go for additive manufacturing. Uh, and especially as I told you, last session, when you use metal forming operations, if you want to have a die, so those are very costly to prepare for each and every product. So that if you have a low volume component production, again the tooling, right? Especially dies, if you want to fabricate that, also it is possible through additive manufacturing. And if the part is so complex, which we are not able to machine it, then this is a feasible method. Okay. Regarding materials, through additive manufacturing, you can see aluminum, cobalt, tool steels, nickel, titanium, stainless steel, all precious metals, copper, and many more metals. Like yesterday, last session, I told, functionally graded material, everything you can just print by this method. This is the base method, powder bed fusion, where you can bind jetting also you can use for metal additive manufacturing. The last method is direct energy deposition. Uh, if you want to go for additive manufacturing of metals, so either you can use powder fusion bed, where spherical powders are being used with laser source or electron beam source, or you can also use direct energy deposition. You can also use the wire arc additive manufacturing. These are the three methods mainly I will focus. I will show as many videos as possible to understand how really it works. Before that, there are a lot of other advantages, when you go for metal additive manufacturing with respect to the conventional method. Here you can see, directly you can have this outer surface. If you see this part, the outer surface is high density, whereas the inner surface is you have low density material. Such a combination of material you can fabricate easily through this process. That is one of the advantage of additive manufacturing of metals. In this part, if you see, the inner core is high density, whereas the outer surface is of low density. Such a combination of different materials, you can just print it. And if you see this gear hub, this is additive manufactured product using powder fusion bed, where you can save a lot of material. You can see this feature, the whole features provided in the gear hub. No, that makes reduced weight. That is also another way which we cannot do by conventional method. If you want to fabricate the same hub, no, it is very costly. So this is directly you can print it. That is also another advantage. This is a aerospace fuel nozzle. This is additive manufactured using powder fusion bed. This is one of the other product, hydraulic crossing block. You can see the features of that. Now you have a whole very thin separate sections. It is easily modeled, and easily you can just build by powder fusion bed. Today, for metals, whatever we are going there are these many techniques available, fusion based and also solid state additive manufacturing. We will not go and see everything, but we will try to cover three base methods. One, I already showed some pictures of powder fusion bed. We will see some videos related to directed energy deposition. And we are working on wire arc additive manufacturing. That also from my lab, I will show a few videos, one or two case studies, what we have done and what is the outcome. And if time permits, I will cover some of the solid state additive manufacturing techniques, which we also work on that, especially frictions additive manufacturing. So this is the laser based DED, directed energy deposition. Where you can have the wire is fed directly to the laser beam source. So once it is melted, the path you can just plan using a CNC control. You can just control that, directly deposit the whatever material. This additive manufacturing is also nowadays popular for the cladding purpose, where if you want to protect the the substrate. By suppose if you take mild steel, I don't want to have corrosion to be dominated. where I can just deposit a stainless steel thin layer on that. This is very popular. No, earlier also it is popular. Now you can just build functionally graded material on that. So this is one method, and this is one video, which is another video where directed energy deposition. This is a nozzle printed on a steel. You can have different combinations of different material and different geometries that can be built by a direct energy deposition. Just some of the components. These are some of the components which people have done, but still we have a lot of scope to do research, especially to control the parameters. Especially if you want to build multi-material systems, and still there is no commercially available machine for like 3D printing for polymers, very popular. Like that, no, there is no low cost machine available till now. But these are the some of the jobs already did by a lot of researchers, and people have done even in production they have done. I will make another few videos for you. This is a very thin section. You are please try to just understand this. This is a very thin section which can be easily built. This is a single mono block. Suppose if you want to build such a system, such a component like this, thin walled structure with a conical shaping, it is not so easy, because you might have to go for taking a sheet and try to weld it. That is one way you can just make this component. This is one of this single component. Whenever your material is not so much deformable, or when the ductility is less, then additive manufacturing is one of the option. So even it is not a straight axis, even multi axis movement. There are machines, even robot with a controller, that can be used for printing the components. Wait a minute. This one. Wait a minute. I'll just stop this. This I will play. Just if you want to, not only complete printing. Just if you want to add something to the top of the system, top of the component. If you want to do some features, if you want to create, still it is possible. That is the one which you are seeing this in this video. Wherever you want to deposit, that alone you can deposit. This is one. So if you consider, this is a 7-axis machine where again it is deposited at it according to the design. Just you just go through this. So this is one video where you will see deposition as well as machining. This is also nowadays very popular, where people used to deposit material and immediately they will go for surface finishing. So because especially this case, since is the pipeline, this pipe kind of material where inner surface is being polished. So this is the one video, what we call it as hybrid manufacturing technique, where additive and subtractive are being simultaneously used. This is one another video. You see, as the title suggests, post processing, you can see a lot of spatter which is on the surface. That should be removed if you want to have the final product. Just even though it is called additive manufacturing, you need certain post processing depending upon the whatever is the source you are using. Either you are using an arc source, or you are using a laser source, or depending upon the base material also. Whether you are the raw material what you are using is a powder, that is a different case. When you use wire, that is a different case. So these spatters you need to remove. This just I will play. They will do some machining. Nowadays, once it is deposited, immediately this spindle will go away. The deposition spindle will go away. Directly, the machining tool will come and do the machining. Yeah. So this is again direct energy deposition, where this is very popular. We are also working on this. There is a cylinder over which you will get radially functionally graded material. So we are also starting with some kind of this work, where we have an arrangement for this rotation. And initially, what we will do, we used to take a cylinder of stainless steel. Then we will try to deposit copper 20% and 80% stainless steel. And next layer will be 40-60. Next layer will be 60-40, 80-20, and finally you will deposit only copper. So such a functionally graded system, if you can develop for pipelines, so that outer surface will be exposed to certain environment, inner surface will be exposed to different environment. So currently we are doing this kind of work in our lab, but this is not ours. I'm showing some work, but we are also working on the similar area of research. So this is about directed energy deposition. We are not working currently on directed energy deposition, but mostly we are working on wire arc additive manufacturing, where it comes under directed energy deposition, where directly your laser, your arc welding sources are being used, where the wire stock is usually it is a metal wire we use, and basically this is the process. So we have to prepare. Wait a minute, I'll just take a pointer. Yeah. Basically, you will start with substrate, then deposition. This is these steps are post processing. See, usually after warm, you may need heat treatment because whenever you do deposition, there may be the problem of anisotropy, which we discussed on the last session by other speakers also. If you have the properties are not uniform along the build direction, then you may need to go for heat treatment. I may give one example, one or two example. If you suppose I will show one picture where we deposited duplex stainless steel. So duplex stainless steel usually consists of dual microstructure. Okay, maybe I will draw this. So this is austenite and this is ferrite. So usually the ratio, if you take 50 to 50%, that means 50% of austenite and 50% of ferrite. Sorry. So when you do melting and solidification, this phase balance is being disturbed. So if you see somewhere here, the ratio may be 70-30. Somewhere here it may be 50-50. Somewhere here it is 30-70. So why there is a difference? Because the cooling rate, because this is here it is a substrate. Whenever you deposit a wall, the heat will be extracted through this. All other places are through only radiation. So naturally the heat transfer, there is a thermal gradient from the top to bottom. Naturally that will affect the formation of the phases present. So the heterogeneity is, this is a microstructural heterogeneity. Naturally, the property also will be different at different locations. If that is the case, you need to go for heat treatment. Okay. Same concept you can apply for any material. Yesterday, last session, I told I use titanium and aluminum for fabricating titanium aluminide. In that case, the composition of aluminum will be different. We just observed aluminum at the higher, on the top it is higher as we progress, but at the lower stages or at the middle stages, the composition of aluminum, the percentage of aluminum is not that much higher. So that will affect the titanium aluminide, whatever we fabricate. That needs, again, this to avoid heterogeneity, we always want heat treatment. This is one post-processing step for if you do metal additive manufacturing. The next thing is machining. Always, whenever you do additive manufacturing using wire or even powder fission bed, your surface finish will be there like this. No, that will be, resolution may be different for different process, but of course you need certain machining. Certain machining you need to do definitely if you want to put it in application. In some cases, intentionally the surface roughness is induced. For example, if you have a collet where you want to create grip, a lot of grip, there is no machining required. Just deposit and directly you can use it. That there machining is not required. Again, it depends on which product and where it is being used. That then we have to decide whether you want to do machining or not. Then substrate removal is nothing but always we start with some substrate where we deposit. It's not like plastics where we will deposit and we just remove from the base plate, which is a heated plate, where always we start with somewhere just you remove this portion. That's it. Then you may need to go for inspection. Inspection in the sense it includes everything. Okay, testing of for radiography, whether there is a defects, porosity. Then you can also go for non-destructive testing, hardness measurements. There are a lot of there that inspection you need to carry out. So regarding the power source for metal additive manufacturing, laser, you have the when you consider arc power, laser is 1/10th and electron beam is 1/30th. The biggest advantage of warm technology, is the high volume deposition. The volume deposition is very, very high. Large component you can fabricate. Say for example, if I will come, when I talk about welding, when I use GTAW process, gas junction arc welding or gas metal arc welding, the deposition rate here is around 2 kg per hour. When I go for GMAW, my deposition rate will be 6 kg per hour. So you just imagine per hour I can deposit 6 kg means that is high volume deposition. When you compare with the laser or electron beam, even powder bed or even it is a directed energy deposition. The other problem in laser is when you have a material like aluminum or copper or where the reflectivity is there. Laser based additive manufacturing is always difficult because the energy absorption is very, very low for the high reflective materials. That is one of the problem in laser. And if you use electron beam electron beam based additive manufacturing, this is necessary vacuum space for fabricating components. Though you have even variation in electron beam, if you take low vacuum, medium vacuum, and high vacuum systems are available for welding. But additive manufacturing for purity, you need to go for a vacuum chamber. That always makes it complex, and also the product size is reduced. So in both the case, laser and electron beam, the deposition rate is low. That is why wire arc additive manufacturing, especially based on arc source, it is high volume deposition. So here, why we want to go, especially high deposition rate, stable process. And if you see the process which is being used for warm, maybe you heard from others, but I will just try to cover and I will show videos on that. You can have gas metal, either MIG or MAG, inert or active gas. If you use CO2, it is called MAG. You can use direct current, alternate current, again based on which material you are going to use. If you use aluminum, especially if you want to deposit aluminum, you have to go for AC current. Because you have, if you deposit aluminum, always there is a oxide layer. For example, no, if you have aluminum here, always there is a oxide layer. Sorry, some problem here. Al2O3 is there. So to avoid that, maybe if you have any doubt, I will explain later. So for aluminum right now, you just understand for the want of time, I'm just skipping this. Aluminum, you always use AC current. Okay, you can just search and understand why it is. If not, I will explain at the end of the session. So you can have Fronius CMT, cold metal transfer, which is very, very popular, where wire is getting retracted after once. So there is substrate, just initially touch this substrate. Once short circuits, there they will just pull the wire back. This they will continue continuously. This is mainly to reduce the heat supply to the weld pull. Okay, so this is very popular. They have a lot of systems developed. Cold metal transfer, it is widely used for additive manufacturing now in industries. There is another process where we call it as tandem MIG multi-wire. That is also one of the process. TIG is very popular. Here, even here also we can feed multi-wire, even 3-wire system we can try, which is not tried by others. Finally, arc, plasma transferred arc, where workpiece is part of the system. That is also another process by which in our center we have both gas metal arc welding based additive and gas tungsten based additive, right? So just to have some brief introduction. So this is GMAW based worm where welding torch and wire. No, I hope many of you studied here in the UG level. If not, just to refresh, I just presenting this slide where you have just a substrate and your arc is created between your wire and the substrate. So you just you can program in such a way that either you can move your substrate if you have a CNC controlled bed. So we are developing such a system now where just your bed can move. You can keep the torch stationary. Even now we are fabricating cylinders using such a technique. I will show a video on that when I just present that to you, right? So this is one setup. This is gas tungsten arc based setup where this is very, very smooth and you will not see such when you use GMW you can see a lot of spatter because the arc is created between the wire and the substrate. Always there is a problem of spatter when you are not controlling the parameters properly. Even then that is not a smooth process. I will show that video how the noisy it is, but this is very smooth. Just wire is fed here to the arc and just try to deposit. Okay, this is again you can you can still play with this. Still lot of scope for research. This process. Okay, you just see this is another video where GTW based. You just see one layer over which other layer is being melted. Just it is being deposited. Initially, you have a layer at the bottom. You can still see there. Maybe I will take laser and show you. This is the first layer. Now, whatever you are seeing is the second layer. So this is the preheating. You can see the feeder. Wire is just fed into the liquid arc column. It is being melted and it is deposited at the rear side. You can see the liquid pool is getting solidified. So one second, I will just. So you can see the capability of worm by seeing the component being deposited here in the first video. Such a big system you can develop. Just only thing is you have to control. You have to develop a system where you need to control the path based on the slicing. Once you slice, you just do the CAD model, slice it. If you have a G code, according to the G code, your system should move. So that control, if you do, then it is easy. This is GMAW. The next picture on the right video is playing. You just see the complexity of the products which are being developed. Any shape, no complex shape can be done. 1 second, I will just play this. Another example. This is a nickel aluminum bronze propeller which was fabricated. It took 3 days for them to do that. This is also being done in some of the institution, even in our country. When I got a project from DRDO, another IIT got a project for developing this nickel aluminum bronze propeller. We are also doing some kind of work on this. Once it is fabricated, always you need to do post-processing. Post-processing, as I mentioned earlier, you need to just, I will play it again. 1 second. So you need to test it. Some non-destructive testing, then just they are doing some grinding to have some surface finish. This is very popular material. Nickel, aluminum, bronze is very popular for ship propeller. Especially these are being made by casting process. where it involves lot of issues like porosity control is very difficult. You need, since it is a casting, the cooling process is very slow. It involves grain growth. Other defects like the grain size is very big. The faces present, if you see closely that material, the faces present in that material is around 4 to 5 faces. What we call it as kappa faces. You can just search nickel membranes, you will understand that. This is a basic setup what we want to have for wire arc additive manufacturing. This is TIG or GTAW, both are same. Tungsten inert gas or gas tungsten arc welding. So just you have wait a minute, I will just take a pointer. Excuse me. So here you have a arc. This is from a wire feeder. This wire is just fed into the arc column. You have shielding arrangement, because once you deposit, if you don't have shielding, this surface will be subjected to oxidation, and your properties, next layer, if you want to deposit, there may be cracks. So shielding is one of the very important thing that is attached to the torch system itself. Though you have shielding gas comes through this also, this is an additional shielding gas cover. So you need to take 2 to 3 lines from the same cylinder, or you can keep separate argon cylinder and just send the gas. So this is one thing. Uh, People have mixed both CO2 and argon also. This is one of the basic setup for that. Uh, this is plasma arc based welding, where the difference is you just keep the tip inside, so that the arc is coming through the nozzle. This nozzle, the arc is restricted. No, the constricted, what we call it as constricted arc. Sorry, constricted arc. Okay. So whenever you do your arc, no, it is not like this. So in case of gas tungsten arc welding, your arc feature will be of diverged arc, where your heat source will be spread across a larger area. In case of plasma, your arc will be a parallel beam where smaller area is focused. That is the advantage of this plasma rapid heating and cooling. So that will help us heat input, low heat input for our system. This is the robotic. Instead of simple automation, you can still have a robot attached to the machine. If you have any machine with you, any gas junction arc welding machine or gas metal arc welding machine, just integrate with the robot. You can use sensors to just understand the mold pool behavior. I'll show some of the pictures which we have done. You need to control with your robot and just to understand how it works. If it even you can use CNC systems, where you can just attach the torch here and just deposit the material. Such a big systems are also available. Sometimes people have tried both gas metal and gas tungsten based both the torch to have large volume deposition at the same time, because as I mentioned here, if you use GTAW, you can go up to 2 kg per hour, whereas in GMAW you can still go up to 6 kg per hour. Both will have different property. So there is another process, cold metal transfer. I'll just play this to understand how it works. You just watch this. You can see it is being retracted. You just watch that how the metal is being transferred. So once it touches, it's called short circuit. Then so this is how one layer over other it is being deposited. The advantage of this process is you high quality deposition there will be zero, almost zero spatter. You cannot see, you are not able to see any particle which is going out of this directly. Once it touches, the metal is being transferred. This is CMT process. You can see, such systems can be used to deposit. You can see a component like this where you can just build a component like this without any problem. See how it works. It is really transferred to drop by drop, and finally you can build a product. No, even with overhanging systems. How it is being built, you just check. This is how it's being built. So this is also possible even with the wire arc. It's like plastics with the overhangings, features. Still, you can do that. So always arc additive manufacturing, you can see the deposition rate, accuracy, and surface finish. If you compare these parameter, arc additive manufacturing always higher deposition rate, but these you have to compromise. You have to tolerate large dimensional inaccuracy, and the productivity is very, very good. Okay, but why the surface roughness is very important? Because any properties, especially if you consider fatigue, fatigue cracks always initiate from the surface. If you have no undulations here, this point may initiate, may act as crack, as the origin, and then it starts from here, and finally it will fail. So always the surface finish is very important. That essentially require surface machining after deposition. So you can also maybe some of other speaker covered this. You can control bead with also the direction. See, you can either you can go this way, only this way. Once you just reach this position, you have to just extinguish the arc, go back and try to bring your torch here, and again you have to start from here. Like that you can go. Uh, or you can use scanning method like this. It again depends on your material. And one more thing, what we can, if you want to deposit a large volume, so there is one more parameter, what we call it as overlap. So you have to overlap the beads. So whenever you do overlap this zone, there is a one particular zone that will be reheated again. So in case of wire arc additive manufacturing, there is no specific term heat affected zone. Instead, there is a term, what we call it as reheated zone. The reheated zone, you need to keep as minimum as possible. So that is very important. So to have some idea about the material which is being fabricated through wire arc additive manufacturing, you can see lot of grades of aluminum. Aluminum, you can this aluminum is, you have different types of grades. No, basically you can classify into heat treatable and non-heat treatable alloys. Uh, Heat treatable alloy is always challenging. Say for example, 2000 series, that is aluminum copper alloy. Sorry, aluminum 4% copper. That is one of the very popular alloy, duralumin, which is used in aircraft. 7075. It is. I'm not able to see any of the work here in 7075 because of the filler metal. Maybe if anyone want to start some work, they can start on 7075. This is aluminum, manganese, zinc, copper alloy. This is a high strength aluminum alloy. If you take the strength is around 540 megapascal, which is much greater than mild steel. So these alloys, in the researcher tried to develop products. If you take titanium, titanium is titanium 6.56A 4B, almost with some alloying. They tried with GTAW, plasma arc. People have tried. If you take steel, starting from mild steel, copper coated steel to different grades of stainless steel is being used by researchers. We are trying with ferritic stainless steel also. Inconel 625, 718, all are attempted through all these processes. Basically, these four processes are very popular: GTW, plasma arc, CMT, and uh, uh, GMW, right? So magnesium still much work is not there. Very less work is there because of the, as I mentioned in the last session. If you are able to get wire from China, then you can do a very good work on magnesiums. No, lot of data you can generate. Still, the data available is very less. Okay. So regarding the hardware system, GTAW, both CNC and robot system, we have both the systems. We have a robotic system and also we have a CNC system to deposit uh, different materials. Plasma, again, same. All these are same. Okay, robot. Either you can use robot or CNC. Whether it is a, as I mentioned, you can see here, 2 kg, maximum 2 kg you can deposit. Plasma 4 kg, GMW up to 6 kg you can go. Tandem wire, if you use multiple wires, you can deposit up to 9 point, almost 10 kg per hour. That is another advantage. Okay, so these are some of the systems. Just this radar plot will give some idea about what are the very important aspects you need to consider when you build components using different materials. You can see here the radar plate, it is compared titanium, aluminum, steel, nickel, all different materials. So how much deformation is there? Whether there is some deformation in there, no, is there? That depends on material. So porosity, residual stress, delamination. Delamination is especially when you deposit titanium aluminide or other exotic combinations. There may be a chance once you build, it will come out of the substrate, or sometimes the bonding between layers they are not very good. Oxidation is other problem where your shielding is not so good, so you have to concentrate on your shielding. Cracking is also depends on interpost temperature. Suppose if I want to build a wall, so once I deposit one layer, the next layer, if I deposit before that, what is the temperature there? That what we call it as interpost temperature. That also very crucial parameter when you want to build a wall or even clad. If you want to do the interpost temperature is very important, where to avoid cracks. Surface finish, again, wall, how much each layer you are depositing, what are the parameters you use, that decides your surface finish. This plot will give certain idea. You can just refer this literature. I have taken it from the literature. Such a system, such a diagram you can generate for your work also. If you take single material and you can just plot all these and you can just produce a result. So to summarize, arc welding machines, only 4 methods: gas junction, plasma, gas metal. Still there are variations within this. Uh, you have separate GTAW or plasma, you need separate wire system that is known. Gas metal or CMT, the arc is between your wire and the plate. When you compare GMW and CMT, your CMT gives you low heat input. The arc stability is very good. The unit is CNC or robot. Comparatively, if you have a CNC system, you need to have control systems to accommodate your G code. Slightly expensive. Robot you can purchase, but only thing is your welding machine should have the capability to integrate with the robot. If it is not, most of the systems, older systems, if you have, then it cannot be integrated with the robot. You can still integrate it externally by externally triggering the torch. Still you can integrate, but when you have synchronization with the your machine, welding machine, then that will be better. Especially there will be problem like, staircase effect. When you deposit one layer, when you deposit next layer, your sizes will get reduced like this. What we call it as staircase effect. This problem you can avoid by integrating your robot with the welding machine through two different methods. One is your robot should have touch sensor. One is touch sensor you should have. The other one, no, you need to use seam tracking. So these features, when it is it is available with the system, then this problem, when you deposit wall, you can still deposit walls like this. So integration of your robot with your welding machine is a very important aspect that you have to understand. So physical process, you can control technical parameters like current, voltage, welding speed, wire speed, substrate temperature, as I mentioned, interlayer temperature. All these, these parameters you need to control. You need to. Somebody asked how to, optimize these. There are many primary and secondary parameter when you take warm. Naturally, you need to optimize the primary parameter, keeping the secondary parameters constant. That is very important. Process monitoring is also important. I will show the monitoring what we are doing in our lab. There are several systems through which you can monitor and you can control the parameter, and you can just control the system. So finally, after the process, what you have to do is you have to control the, you have to measure the residual stress. You have to scan it and understand how much porosity is there, but you should avoid porosity each and every layer. Cracks and delamination is one of the very big problem, especially when you go for multi-material system. So application wise, you have a lot of application. You can see, you can just put a Google search. You can understand how very big components. I will show some of these mentioned here, which I have taken from literature. Here, as I mentioned, what our future prospect is this. There is a lot of data which is required. Modeling aspect, someone whoever is very capable in modeling, they can start modeling of additive manufacturing. That is, there are a lot of scope. Some YouTube channels are there. You can just search for that and learn how you can understand the material transfer, how you can relate that with the metallurgy. Those aspects need to be done. Hybrid additive subtractive technology, especially some videos I showed where deposition simultaneously you need to do machining. So that is one technique very important. Yeah. Somebody asked just last session, AI guided warm technology. You can still go to that same thing. You just this is one with you just see there is a arc created once deposited. Once the deposition over, there will be a roller which will come and compress. This is mainly to create compressive residual stress. Because whenever you melt and deposit, always once it solidifies, you can see the tensile residual stresses will be induced but whenever you have tensile residual stress, that is not acceptable, that is not desirable when you consider fatigue loading. This is one hybrid method. You just see one deposition, then they will just use a roller, just compress the material deposited. Here two things. One is to have compressive residual stress. Other one, no, always when you deposit, right, the bead will look like this. If you slightly compress it, your bead will it will get this feature, so that your surface finish will be improved. You see, just imagine this deposition once it is compressed. Just if you deposit like this, you see there is always surface roughness here. You can see here. This is the surface roughness, right? But that is also one of the advantage of this, in addition to the compressive residual stress. That is the because whenever you do weld or additive manufacture, if you have a crack here, when you try to pull it, if you have, suppose if I applied 200 kilonewton here or 20 kilonewton here, already I have 10 kilonewton here, say for example 20, that is positive. Actual load applied is 220. It is not 200. But we think it is 200. But tensile residual is there. It is 220. But we have to consider that into account. So naturally, this will help us to compressive residual stress. If it is minus 20, just imagine even if you apply 200, that will become 180. So that is the advantage of this process. So a lot of, if you see Cranfield website, you can see this wing spare, which is fabricated using additive manufactured. This is landing gear. No, this is a NASC titanium company. They fabricated this. So a lot of application you have on WARM. This is BAE system where high strength steel wing for wind tunnel testing. They use the CMT process. You can also see the hollow features deposited. You can see this is around 400 millimeter. It's made up of mild steel. It's a truncated cone. You can see a feature deposited here. Just I will have certain some video. Yeah. So here the table is moving. We are keeping the torch stationary. Both we can do. Now you see the here in this case, your head is moving. Now we actually they are doing machining. So end milling they are doing, right? So this is another video just to show the capability of the process. Yeah. So we in our lab, we are doing a lot of work on different materials. We are working. This is gas metal arc welding based additive. We deposited duplex stainless steel. This is a duplex stainless steel. This is after machining. I have this video. I'll just play it. You just see, since the arc is created between your wire and the substrate, the previous layer, you can see the splatter which is coming out. This setup we have, we fabricated this setup. We have the system. Almost we deposited different materials, starting from mild steel to different grades of stainless steel. Even nickel, aluminum, bronze we deposited. So our objective is to these people have done walls, but cylinders very only one literature is there. But this is a thick section. You can see still you can oscillate the torch and able to get 15 mm thick. This is the 15 mm thick cylinder. After that, we do this. This is a boiling MgCl for 154 degrees centigrade MgCl boiling setup, where your material is subjected to high temperature, 150 degrees centigrade. At the same time, it will be loaded. So this setup is available. We have done now almost two of my students completed their PhD. Currently on additive manufacturing, almost we are working on different materials. All stainless steel is being tested for this test. So we also, this is the machine which we designed, and it was supplied by this supplier. You can have the torch here. So this is the nickel aluminum bronze which we deposited for some other purpose for erosion corrosion studies. These two are we are working. We almost did 15 different cylinders, and each cylinder is subjected to different studies. Okay, not like conventional studies people used to do. No tensile test, hardness. That is not sufficient for publication, or the novelty is being questioned. So this is the next setup what we have in our lab. You can see the power source here. I'll just take my pointer. This is my power source. This is the Miller Dynasty 350 machine, which is capable, of pulsed current welding. You have a lot of parameters which you can control in this machine. You can see this is a work table. It is attached with a robot. We have two wire feeders, one here and one here. This is basically, we did it for, 1 second. I got a call. Hello. One second, sorry, some problem with my, I'll just go on the Discord and come back. Are you able to see my slide now?
Yes, sir. Yes, sir.
Yes,
Sorry,
sir.
sorry.
Yes, sir.
Sorry.
Yes, sir.
Yeah, please, wait. Okay, right. So did you see this slide or what? Did you see this slide on nickel aluminum bronze or boiling setup? Where have we left? Where have we missed it?
That video, sir.
This one?
Yeah, correct.
Okay. Okay, this is the GMW setup which I just shared now. Now this is a boiling setup for SEC. Just I explained that already. You just watch. See the condition here. No, it is boiled. No, this is a magnesium chloride solution. It is boiled at 150 degrees centigrade. We apply load from the top, and we also measure the elongation. So this is the nickel aluminum bronze which I shared. We used to do for erosion corrosion testing. So this is one setup what we have. So in between, if you are not able to see slide or if you feel disturbances, please let me know so that I can there itself I'll correct. Okay. So this is a Miller Dynasty setup, GTW setup, and we have two wire feeders, and we did it for aluminum and titanium. Now we are doing it for different combinations. This is with the thermal camera, imaging camera, we are capturing. You can see two wires which is fed into the R column. We also monitor the sound signals so that we can just compare defect-free beats with the defective beats. So by seeing the count, we can directly do online monitoring. Such a way that we can avoid defects. But still, you can apply machine learning algorithms to train the system, and you can just create online monitoring. Okay, just this is a video which you can just see. This is a robotic arrangement in my lab, just to deposit both wires. So you can do programming and you can just build wall. Even curved surface you can do, but since it is a two-wire system, we are facing some challenges. We have taken up a project where we are working on that. Otherwise, if it's a single material, it's not so difficult. You can just deposit and you can just continue your work. Even closer look I will show. Next slide, I have another very simple closer view how your material is transferred to the system. But this is a very smooth process. No, you cannot see any. You just see here one side it is titanium. You can see this is a wire which is going here. This side it is aluminum. I'll just play this video. You can see how it is being mixed, right? I'll just play this. So you can still see that there is a wire coming from here. There is a wire coming from here. You can see the deposition here. So this is the tungsten tip. This one is tungsten. I'll play it again. We just watch it. So now we are thinking of to go for third wire to have to understand really what is the effect of ternering and whether we're able to mix it. That we have to check. This is the thermal imaging we did. You can see the torch is going up. Robotic system. Once it reach, we can directly record the temperature. You can get cooling curves from each and every point, starting from this point wire and this melt pool, and just around the areas, you can just construct the cooling curve, heating and cooling curve from this. So the limitation, maybe I will have another 20 minutes. I will quickly just go through solid state also. The fusion is always whenever you just melt and deposit, always it suffers from metallurgical defect. Say one example is cracks, porosity, all these comes into picture. So solidification related defects is always a problem in fusion based metal additive manufacturing. People have started using solid state technique, basically rotary based. I hope you all aware of this as an engineer, mechanical engineering student, faculty or student, mostly faculty, right? So friction welding is being used to join rods. That is currently being used for just I will cover these three process, then we'll just see. This is linear friction welding where again, instead of rods, we just use two members, just oscillate and try to join. Why I'm covering this? Because based on this, people have developed additive manufacturing and developed components. This is no, instead of rotation, it is oscillating. This is linear friction welding. This is friction surfacing. Okay, just a deposit, just instead of the non-consumable tool, they will use a consumable rod. The substrate is harder than this rod, or even equal. So they will try to deform the material and try to deposit. Maybe this kind of work is being was carried out by Dr. Karthik, who presented few days back. He gave a lecture. He did some work on that. His literature also I have. Maybe I will cover. So just a deposit. This is a consumable. Just a deposit. Like this, you can deposit in solid state. Here the material will never go to its melting point. So naturally, you will just deform the material which is below solvers line. Try to deposit. So this process is very, very popular for joinings. Aluminum, it was developed for aluminum, but it was then extended to almost every material, including high temperature materials. So just use a tool, deform the material, just to try to join. We are not going to use this way for additive, but once you have to keep stacks, try to do joining. I did some work using this friction based additive manufacturing. You have a lot of processes, friction stir additive, linear friction welding based. One very popular nowadays it become, because the machines are not available in our country, but some Western countries, they are doing this additive friction stir, or in other words, there is a company called Meld who do work on this process and developed a very beautiful system for aluminum. Okay, so these are the methods by which this is the work of done in IIT Madras, a very few years back, long, almost 15 years back. So they just used friction welding process just to deposit one layer, then another layer, then another, like that. They just built the system. This is one thing. I told Karthik, right, who presented, he did some work on this on 5083 metal to metal composites. Somebody asked metal composites. So that he developed such a system. Almost now it is 9 years back. Additive friction manufacturing by friction surfacing is one of the technique where you just deposit, as I showed the video, consumable rod, just just touch the substrate, create friction. That friction will create heat by plastic deformation. Then that will be deposited on the substrate. So one complete one over another layer you can just deposit. This is one of the Martin 6 stainless steel deposited again IIT Madras very long back. People have gone much better than this now, but just to show that done much earlier. So there is some other technique which is used to complete the grooves also. I'll not go deep into it, considering the time. Maybe I will just to go through friction. These are work some very long back when I did PhD. We did it for WRI, Welding Research Institute. We did cladding, even yeah, SSN. We tried aluminum on the top of aluminum. We clad magnesium. It was published in 2017. Even bend test showed good results. I don't want to waste time. So this is the one process we are working right now on magnesium and do some creep studies. So friction additive manufacturing is layer by layer. It comes under, I covered 7 process. It comes under sheet lamination. So take a sheet, keep one over other, just to do friction stir welding. You can just overlap. Just I will draw it. Wait a minute. I will just quickly. Wait a minute. Yeah. Sorry. Sorry. Okay. So to complete thing, no, you can go like this. I did 4 layers now with magnesium. You can weld like this. Okay, this is friction additive manufacturing. You can see which I have taken from literature. This is for 7075. You can still watch this video to understand how it works. Now they are doing friction. They are doing welding only, but they are stacking material and doing welding. Then they will do machining. You see just size of that product. If you want to build such a product using wire arc additive manufacturing, then imagine, it is a melting process. There are 2 problems. One is size. You can do that by wire arc additive manufacturing, but you need to spend a lot of time. You are involving a lot of energy. And other problem is the properties will not be so good as in this case. So this is one process which is not there listed in the most of the net. If you search sheet lamination, they say ultrasonic, but they are not covering this. But so you just layer by layer, if you see, you can see the cross section and understand whether there is a defect or not. This and all. No, you can see this 9-layer build where you can see one over other over. You can see the macro structure. Understand? This is a 7075 component. There are other applications. It is being used for stringer application where you want to join 7075 with 2024 and some nuclear applications where you deposit P91 with some stiffeners for heat high temperature application. So I will skip this and directly I want to show one aspect. This is the process. Okay, this is very important process. Now I will show 1 or 2 videos. So they will be sending similar to friction surfacing, but through spindle. See, they are spending filler rod, or even they will use powder and compress. They are depositing continuously this material. So there is a company called Aeroprobe. They uses they patented this technology. One of the Indian who worked PhD IIC Bangalore, he was in the patent when he joined Aeroprobe. This process he worked. But this is currently being used in they're very popular by a company called Meld. You can see the how the chip is being converted. Even for recycling, this is very useful process. Especially, I told you, magnesium alloys. If you have a lot of chips, then you can just put this, like a screw injection molding. Just put this uh, scrap inside or the chips inside, where it will be, go to this place and it will rotate. Thereby, friction is generated, and you can just heat it, just make it to semi-solid state, and just try to deposit. This is one process, very very popular. What we call it as additive friction stir. This video will give you some idea how it works. So very nice. This process is, because these machines are not available in India. I'm not seeing any machines in India this kind of work. If you develop machines, this is one of the work, one of the mission, one of the research. You can do it for especially magnesium and aluminum. This is a very good process, but people have tried it for titanium also in Western countries. So this is very dense problem. No, if you do wire arc additive manufacturing, the properties, whatever you get through this process, you will never get. Uh, Especially, the ductility. The ductility is very, very good. The grain size is small. It is not a EQ-axed grain size instead of dendritic grains. So that is the advantage of this process. You see the other one, some more videos just to give glimpses of how no this process is useful. They are depositing. This is a titanium on the top. It is titanium. They are doing it for cladding. Okay. So the grain size, you see, this is what you see. The very fine grains you will see. No, even it's like a rot structure. No, basically microstructure. If you see cast structure, rot means secondary process. That means deformed. Cast means just melt and solidify. Always use this for better properties. So that is why these are some of the cylinders. There is a company called Meld. They do a lot of work on this. You can just watch this. Just type Meld. You can get a lot of inputs for this. Especially these propellers. If you have some cracks, you can just modify that. You can do repair work using this process. No, you cannot throw it out, because since there is a crack, you cannot spoil the whole propeller. Instead, just repair it and you can use it. Right? This is one thing. Some more examples are there. You just see this. I will just to conclude. Here there is a powder fusion bed at the bottom. The accuracy is this much microns you can control, 20 to 60 microns you can control. But if you see, the build rate is very very low. Here it is around directed energy deposition. You can control up to 100 to 200 microns, but you can up to 5 to 6 kg per hour. You can deposit, but still additive friction still you can see up to 12. There are a lot of advantages for additive. One aspect is deposition rate is huge. Property wise, you have excellent property because your material is subjected to secondary processing, especially deformation at high temperature. You will get excellent property, right? So to conclude, solid state, lot of applications are there. Linear friction deposit, all with the same principle, with the geometry is different, right? With this, I just conclude, because if you have time, because so this is my center. You can visit my center whenever you want. Uh, if you want to have some collaboration also, based on the availability, just we can collaborate, or based on the problem we can collaborate. Thank you very much. Just
Thank you, sir. Thank you.
Yes, ma'am. Yes.
Thank you, sir. Thank you for a wonderful presentation. Now we'll open up the session for any queries. If you have any queries, you can post in your chat box.
If you have anything, any work you want to start or anything, any doubts also you can ask. Anything related to materials you can ask. Which material you can select? What is the current trend? If you want to know something on that, you can ask.
I think no question from audience side, sir.
Okay.
Actually,
That's fine.
it is a pure demo. Actually, some question has comes in the chat box, sir, now.
Yeah. You just check, sir. Oh, yeah.
Composite materials application.
Where it is there? Today, composite material application. Huh? Yeah, you can do. No, see, I told you, no, the composites, you can do it in two different ways. One is just use some wire, deposit a layer, then you make a groove. There is one aspect which is still open up for research. Just deposit a layer, make a small groove, put the reinforcement, again deposit another layer. That this is a hybrid method by which you can make a composite. You can just search, some work has been done by people on steel and reinforcement, aluminum and reinforcement. Just deposit a layer, make a groove, small groove, fill that groove with secondary particle reinforcement. Then you just deposit another layer. Okay, this is one way. The other way, what we are doing is in situ formation. Composite is in situ formation. So add element. No, two wires we are using. That itself, there will be alloy formation. If you want to add certain element, you can just add it to the melt pool. Use some feeder. At a constant rate you can feed, or you can also use some foil, or even reinforcement of any shape. It may be a particle shape, or it may be a foil shape. Just do that. You can make a composite. That is thing. Okay. So see, I'm not working on ceramics. The intermetallics I'm working. Okay. Ceramics I'm not working. Composite material from waste. That's what this process, additive friction stir. We don't have machines for that. Waste to directly convert from waste to wire arc editing manufacturing, I'm not able to see anything. But for additive friction stir process, where the chips, right, machined chips are being reused. Okay, we did some work on, I published some work on, friction stir extrusion, where we fabricated a magnesium tube from waste. That means machined chips. Okay, that we can even wires you can generate. That can be used for welding of magnesium alloys. Those are there, but that is not. Yes, you can do that. Wires you can fabricate. You can call it as layer by layer. If you just prepare, you can call it as additive. But it is a process called friction extrusion. There is a process called friction extrusion. There, the machined chips are being reused by making it as a wire. So that wire you have a lot of application. So that wire you can again reuse it for welding. Okay. So those are the application. Composite area is wide open now. Composite still people see only people tried single wire, different materials people used. Two aspects. One, you have to change the material, but almost every material is now published by somebody. Now what we can do is you can go for different property evaluation, that you can do, but the only thing is again you will face is the facility. Okay, suppose if I want to do fatigue, So I need to search for fatigue testing facility. If you go to a lab, they will charge, very high. So only if you have facility, or if you are looking for some collaboration with the people who are already having fatigue, then you can do that. So creep studies, corrosion studies, stress corrosion cracking studies, lot of things you can do by evaluating different properties. Other thing is modify, different material, combination of material that you can do. Composites also one of the area, which will, we can publish. Even 100 papers already there, still 101st paper will be yours if you work on it properly.
One important question is there in the chat box, sir.
I need to do some mechanical testing. If the facilities are, is it see the thing is, simple testing facility, people always cost, our center is charging, okay, for tensile testing or whatever testing you want to do, we are charging. That is one thing. For advanced facilities, no, because the SEC and all, if you want to test, boiling setup itself, it will take 5 days to complete one test. Okay, and it involves lot of consumables. See, magnesium chloride, so you want to have the heaters, life of the heater is there. So those tests, we can do it in collaboration mode instead of cost basis. For basic testing, we have facility, but they will charge minimum. You can do that. We have mechanical testing. We are going to buy harness test. Even scanning electron microscope is there in our college. It is a centralized facility, but they will charge. They will charge, minimum level. But slots you can get, you can just do that. Mechanical testing, then you have to tell what type of test. Harness test we are going to buy. We already placed order. Tensile test machines we have. We have 2 tensile test machines, electromechanical control machines we have. We have facility for casting, bottom pouring, furnace. We have other facilities which I have not showed. We have other facilities we have. Okay, based on your need, we will suggest. Wear tester we have. Oh, it depends on the need. Okay.
That's all, sir. No more questions.
Thank you.
Yes, sir. Actually, it was a very good presentation, sir. Actually, we all got an real-time experience of how the 3D printers are working and various parametrical constraints and how we have to choose a particular machine for our applications. All those things you have explained elaborately, sir. And so many feedback also coming into the chat box, which shows that how they are inspired your presentation. Thank you, sir. Thank you for your wonderful presentation.
Thank you very much. Actually, I want to thank the organizers, the whole organizing team, for having me here to just share. Lot of work we are doing, but no, you can visit my lab. Whoever is nearby, you can visit. My lab and understand what because we have a display there itself. You can just check and understand. We mostly do work on welding. We did a lot of work on friction stir welding. We have done a lot of products also, especially copper to aluminum heat sinks, bumpers, lot of things we have done. Somebody asked dynamic testing of material. Just I want to tell that we did some work on crash worthiness. That also there, but not on IAM materials. We did it for steel weldments, FSW welded by FSWs, which is not yet published. We are on to the work to publish it maybe in future. Additive dynamic properties we are not doing. In fact, we are going to do that for duplex stainless steel dynamic drop weight tester, which is available in IG car. See, most of the test we don't have facility. Even for creep, we have facility for low melting temperature materials. Up to aluminum we can do, but for duplex stainless steel or high temperature material, we are depending on our collaborators who are in IG car. We published a few papers. Some of my PhD scholars who completed PhD, they use facility of IG car. So if you have some collaboration with those people, then you can do wonderful work. We are going to do some work on that drop weight, impact. that is dynamic loading. That is the first work we are going to do. Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
So with this,
Okay,
we can
maybe-
conclude that first session of
Yeah.
today's FDP. And
Thank you.
Dr. Lakshminarayanan sir has given extended elaborated support for this FDP, and tirelessly he taken 2 sessions in this FDP. It is really a very tough task nowadays, sitting in front of the system continuously for 3 hours, put together the 2 sessions. Thank you, sir. Thanks a lot.
Thank you very
for
much,
your
sir. Thank
support,
you.
sir.
Thank you. We will meet at some time. We will meet.
Yeah,
Thank you, sir.
Sure, sir. Sure. Thank
Yeah,
you, sir. Thank you, sir.
Bye. Bye. Thank you. Bye. Sir.